the meeting and be a part of the process moving forward. So let's move to the next slide. We're going to go pretty quick. This is a 5-minute overview. Some of you already know a lot of this. Basically, we started in January of 2020, thanks to Don Crocker and the Wildlife Conservation Board. And we've been progressing. We've completed the limiting factors analysis, a conceptual model for steelhead for the entire watershed, including the upper tributaries, Arroyo Seco and Tujunga, all the way down to the ocean in Long Beach. We are currently at this red button. We are here. You are here with us, and we're going to be moving from here through a completed basis of design report draft, end of March. You will see that. We will send that out. And then we'll be segueing to a very integrated process, working with folks like LA Metro, Metro Bikeways, the Arbor, and the county, and all of the other city connected projects, trying to integrate and move forward into implementation. The scope of this grant is looking to be complete this year, winter 2021, with a 60% design. Completion of an initial study. There will also be CEQA NEPA scoping, and the appropriate environmental document would follow. Next slide. So overall, we have great progress, and I'm not seeing the next slide. Okay. I think there's a lag. I'm just going to talk. Okay. So there are a lot of design tasks. I'm just not seeing it, but basically there are. Oh, it's the project area slide. Okay, so the top of the project area is basically the soft bottom of the LA River, just past the Arroyo Seco confluence, where it gets into the Glendale Narrows. So from that point down past this confluence, past Piggyback Yard to the Washington Boulevard Bridge. So basically a 4.8-mile stretch that is within the city of LA limits. Overlaps with the Army Corps' Arbor Reaches 7 and 8, and is entirely concrete channel. So this really is a pilot. It's a moment in history to bring back natural features to the river and to facilitate migration of steelhead. Okay, the next slide is design and recommended environmental tasks and into construction. So we talked about the limiting factors. You'll see a little bit more highlight on that in the slides that follow. Basically in the design phase, we're going to be walking you through some of the results, looking at major constraints for flood protection. What does that mean for this project? And then also looking at other opportunities, how we can dovetail with things in the design dialogue and other projects. And then finally, into the environmental, you see a whole slew of your typical CEQA checklist items. In particular, we're going to be continuing to focus on outreach. And so one of the major players, of course, is our own tribal, Native American advocates for fish passage, and they will be part of this process moving forward. And then into construction. There's been, of course, many permitting agencies, CDFW and U.S. Fish and Wildlife and NIMS in particular have been really helping us with the steelhead needs and just really bright thoughts about what we can do given this real novel project. And again, the county and the regional board and others are very focused on how we can integrate with their work. Next slide. So, okay, so yes. So still water, and many scientists really love to dig deep. So we did. We took a deep dive into for steelhead in this watershed, in adjoining watersheds, and just throughout its distinct population segment throughout Southern California and in our northern watersheds to understand the life history needs, species, the full stressors. We all know we have a lot of things with climate change and water needs, watershed characteristics. You know, we have great habitat in the Arroyo Seco, and this led to a conceptual model and an understanding of the limiting factors for the species. The outcomes are really important towards watershed health. So our future generations with all related recreation and water needs, water quality, and so forth. There's a huge opportunity. Okay, I'm hearing that you're having trouble hearing me. Let me try taking off video. Okay. The passage window for the fish is something that's very critical when we think about how much water do we need in the channel for the fish to migrate. What does that really look like? How many days do they need? So basically, the adult migration from the ocean to our project site, which is about 20 miles, would take 2 to 5 days, depending on how fast the fish is and what obstacles they may hit as they travel. On average, about 6 days to reach the Arroyo Seco. So that's kind of the overall picture. And there really are multiple events, kind of like what we're seeing now with our storms. And so we need holding areas. We need areas where the fish can hunker down, take refuge before the next storm system and their next sprint. So limiting factors for this watershed are similar to almost every watershed where steelhead are historically present or were historically present. Altered flow patterns. There are barriers to upstream migration, such as Devil's Gate Dam. There are high water temperatures during the summer. Not so much right now, but during the summer. The fish move typically in the winter. Spawning and rearing habitat in the tributaries is a green. Good news. There's lots of great habitat that's existed for millions of years and is still there. Next. Opportunities and constraints. Great. So now Isaac Brown will walk you through the opportunities and constraints for this project.
All right, thanks everyone. Good morning. So yeah, I'm gonna talk about constraints. I'm also going to talk about opportunities and really what all of the kind of surrounding context and constantly evolving surrounding context to this project and how we've integrated that into the design. So next. So we're looking at we've inventoried all of the design work, GIS data layers, constraints layers, things like downtown design dialogues. We've taken a careful look at all of kind of the big idea design concepts such as this one here at the Arroyo Seco Confluence, and really trying to just anticipate what's possible in the future in this reach and design both for the fish science, but also to have some flexibility for accommodating what's possible. This is a great example of an important connection. I think next slide, where if something like the previous project were to happen, you might achieve a connection between Arroyo Seco and Elysian Park, which is a key connection for the broader rim of the valley corridor. So that's just one opportunity to the project, and so we're kind of designing specifically around the Arroyo Seco confluence. You'll see in a minute the idea of a confluence pool. This was a an important feature for steelhead. Often at the confluence of tributaries, they would often hold there and wait for the next storm and move up the tributary. So we're designing for things like that and anticipating potentially even more connections in the future. Next slide. Of course, we're integrating with the Arbor Plan. Key projects where the river interface is very significant with Arbor, which are the cornfields and piggyback yard. Next slide. And also, this is more on the big idea end, opportunity end, the LA Sand rehabilitation of Hollenbeck Lake, which is down toward the south end of the project along the 10 freeway, just north of the 10 freeway. So there's going to be improved water quality in this lake, which feeds into a creek that's currently in a pipe. However, that heads through, could be restored through LA Sand property. We've thrown this idea out there, not necessarily going to happen. However, potential. So we're looking at that site for another possible confluence pool in anticipation that something could happen here. Next slide. Even bigger ideas, looking at the potential for those confluence pools to potentially connect with tributaries in the future. So we've got some pretty significant tributaries, the most significant being this Hollenbeck Creek, Arroyo Seco, of course, is the main one, but Hollenbeck Creek, and then at Piggyback Yard, there's another trib coming out of Ascot Hills. Could we in the future potentially create some high quality habitat in those creeks? And there's kind of an open question right now about whether steelhead may have even spawned in the Elysian Valley and further south in the mountains in years where it was a dry year and they couldn't get up there. They found themselves in the Elysian Valley and perhaps they spawned there. So, maybe this is something we can redesign into the city fabric, or possibly as an interim solution until we get up to the mountains as a potential spawning habitat. And I'll just say this is the concept and an old concept for Taylor Yard. This is not the plan for Taylor Yard right now, just showing the idea here. Next slide. And yeah, like Wendy mentioned, we're integrating with LA Metro. They have designs for the path that are, more preliminary than ours, but they will be altering the channel bed with columns, bridges, and the channel walls with the bike path. So that will alter the hydrology and the hydraulics of the river. So all of our design and modeling for flood and fish passage will need to accommodate that as these kind of plans evolve together. LA River Master Plan update as well. Next slide. And so this is just kind of a screenshot of a collection of our data layers that we've pulled from various sites. These are power lines, sewer lines, transmission lines, all the things that are happening under the riverbed, adjacent to the riverbed, that we'll have to think about as we design. So we've got this. This is kind of right there with the whole design process. And if you're aware of anything else that's not on this list, we really want to see it. And I think that's the end of my section.
Thanks, Isaac. So now Ed Wallace will walk us through the basis of design. Ed?
Yeah, good morning, everyone. I'm going to talk about some of the key hydrologic and hydraulic and engineering considerations that go into the basis of the 30% design. And I'll just start with a little bit about the existing conditions. We have a channel that was designed to very efficiently convey flood flows, but it operates at very high velocities, generally in the supercritical flow regime, and for more frequent flows at very shallow depths. So there is a low flow channel in most of the project area, but it's generally about a foot deep, so very shallow. And then as flows increase, velocities also increase. The graphic on the right is showing a comparison of the existing hydraulics. So that's the curve on the bottom, and conceptually just showing that what happens is when we reach a depth of 1 foot, which is the minimum that we would minimum depth that we would design for steelhead passage, velocities are already high. And then as depths increase above that 1 foot depth, they get into the range on the right side of that chart that are unsuitable for steelhead passage. And so our challenge is really to change the hydraulics of the channel to be more like the curve on the left and operate in that left-hand square there where we have lower velocities and higher depths that are suitable for fish passage. And of course, the challenge is to do that while also not having an adverse effect on flood flows. Next one. And so this is just a video to kind of illustrate what we're trying to achieve. This is a video taken from the Main Street Bridge in the late January flows. And it's hard to see the velocity, but you can kind of get a sense of it from the wave on the leading edge of that pier. So a standing wave there, a foot in height, relates to a velocity probably about 8 feet per second. And so under existing conditions, can you run the existing conditions simulation? We're just showing, if you can see in the gray there, fish trying to ascend, but without any cover and in the high velocity tiring and falling back in the channel. And then what we're trying to achieve, a roughened section of channel in the center there that provides lower velocities and cover so the fish are able to ascend a portion of the channel. Next one. So the design approach is a roughened channel that would be inset into the existing concrete flood protection channel. And the channel slope, the existing channel slope is about 0.45%. That's actually relatively low for this type of a fish pass. Roughened channels have been successfully implemented at slopes up to 4 or 5%. So it's not a particularly challenging slope. We are following CDFW and NIMF's guidance to develop design flows and for the criteria for fish passage hydraulics. And we are focusing on upstream migration for adult steelhead. That was identified as a limiting factor. So really focused on transit for adult steelhead to get to the upper watersheds for spawning and rearing. And the two graphics on the bottom, the one on the left is kind of showing that for a given area, a given channel area, fish passage and flood protection are sort of at odds with each other for in terms of roughness. Higher roughness is better for fish passage. The higher roughness we have, the better fish passage conditions we have, but it affects flood protection. And the graphic on the right, for the same roughness, the thing that helps us for both flood protection and fish passage is increased channel area, increased conveyance area. So the basic approach is to add roughness to improve fish passage, but compensate for that for flood conveyance with increased flow area. Next one. And just a little review of how we got here. The Bureau in 2019 did a study that looked at fish passage in urban flood control channels using numerical modeling, especially looking at things like boulder clusters and channel shape and projections that provide velocity cover for fish passage, but also using the physical model for that purpose. And then the design team, a graphic on the lower right is showing one of the initial concepts that was developed by the design team for this project. Using 1D models, we developed several concepts that provided an inset channel with a roughened surface to improve fish passage hydraulics and at the same time not have an effect on flood water surface elevations. Next slide. And then more recently, we've been working on concepts or refinements of the concepts that introduce hydraulic diversity into the channel shape of the low flow channel. The cross-section shape itself affects the velocity distribution. And so we considered multiple options for more complex channels in 1D RAS models. And we've selected an asymmetric shape for the typical sections that have been carried forward in the 30% design. And the graphics on the bottom there are showing sort of a simple channel with the velocities in the channel indicated by color. So you can see in the simpler channel on the left-hand side, we get not very much hydraulic diversity in the channel, and as flows increase, pretty much velocity increases everywhere in the channel. And in comparison, the graphic on the right showing an asymmetric section or a variable section where we concentrate the lower flows so that we get adequate depth for fish passage, but as flows increase, we get more velocity zones in the channel, so that even though we might have high velocities in the center of the channel, we maintain areas on the shoulder of the channel with lower velocities and adequate depth for fish passage. And this is really a lot more like the way natural channels are formed and perform, and it gives us more hydraulic diversity and better performance across a range of flows for fish passage. Next one. So this is how the asymmetric cross-section shape looks in an illustrative concept. The bed of the channel is a fixed bed, but with roughness elements of cobbles and boulders. The bed needs to be fixed because of the very high velocities and shear stresses in flood flows. But we are looking at ways to provide openings in that fixed bed for herbaceous vegetation to grow. Vegetation would be selected to be plants that would lay down in flood flows and have a minimal effect on flood conveyance. And we're also looking at ways that we can accommodate or maybe encourage the accumulation of natural bed material in the channel. Next one. And this is, so that the concept A was a 44-foot wide by 5-foot deep channel. We also have a concept B shown here. That's a little wider channel, 60 by 4 feet deep. And these are the typical sections that through much of the project reach we've carried forward and evaluated in the two-dimensional model for fish passage. Next one. Okay, so just to illustrate how this might look, this is a typical section of the LA River, I think, from the 6th Street Bridge. And the next slide showing how that inset channel might look in the same area with the channel set into the existing concrete channel. Next one. We do also have a major opportunity at Piggy Backyard, as Isaac was saying. This is in much of the project reach. We are very constrained by development and rail lines along the side of the channel. But the Piggy Backyard is an area that the Arbor Plan had a restoration plan for, and the design team has developed and tested in the hydraulic models a concept for a much wider channel here. And it's really a unique opportunity to provide more habitat in the project area. And from the passage objective, it provides a place where fish could find flood refuge. We know we have very flashy hydrology and flows increase and decrease rapidly. So it would be a place where there would be refuge from high flows for fish to wait for a peak to pass and then continue on upstream as flows recede. Next one. We are also thinking of ways to incorporate resting areas in more of the typical sections or in the areas where we're more constrained. And the Bureau really sort of started this with the 2019 analysis, mostly looking at boulder clusters and projections and channel shape that provide velocity cover. But right now we're investigating options that are more thinking about sort of negative space, pockets in the side of the channel or pockets in the bottom that can also provide resting areas. And of course, the advantage of sort of cutouts like that is that they're added area instead of projection, so potentially reduce flood conveyance effects. And of course, we do have the major opportunity at Piggy Backyard for resting and flood refuge. Next one. Okay, and Isaac mentioned, considering that flows, the timing of flows is sometimes offset between the main stem and tributaries. An important place to think about resting and refuge is the Arroyo Seco confluence. So we've developed a concept there for larger pools at the confluence or just downstream of the confluence. And this concept was developed into a design. That terrain was then used in 2D modeling, and we'll show the results in the second half of the presentation for the 2D model results to show velocities and depths in this area. Next one. Okay, I'm going to dive a little bit deep now into some of the details. Fish passage design flows. Really, we're doing this based on CDFW and NIMS guidance. And it's based on gauge analysis for the nearby LA River and Arroyo Seco gauges. We're using the gauge period that we think represents the current hydrologic regime, so that's 85 to 2019. We also looked at hydrographs in addition to gauge statistics just to get a better sense of the passage window, the window of time available for steelhead to pass associated with selecting a particular design flow, especially the high fish passage design flow. And again, we are focused on upstream migration for adults. And from the NIFS and CDFW guidance for steelhead, the low fish passage design flow is the 50% exceedance flow in the migration season. And the high fish passage is the 1% exceedance. So 50% exceedance means that's the flow that's exceeded 50% of the time. And 1% exceedance means it's a flow that has exceeded 1% of the time. So 99% of the time, the flows are below that 1% exceedance. And we know there's a preference to look at the 1% exceedance in the migration season. That gives you a little bit higher flows than the 1% from the entire record or the annual record. And so we are looking at that flow. There are other flows in the guidance that relate to juveniles and non-salmonid species, and we'll see a little bit of that in the next slide. And so these flows, we really want to, even though we have a high fish passage design flow and a low fish passage design flow that are shown in bold here, that are maybe the most important to look at, we really want to look at a series of flows to see how concepts perform across a range of flows. So this table, a series of flows, was developed mostly from CDFW and NIMS guidance, and some of the statistics here relate to juveniles rather than adults, or native non-salmonids rather than salmonids, but still they're useful so that we can look at performance of these concepts against a range of flows. And the one on the top there, the current low flow conditions are affected by wastewater treatment plant releases into the river, and we want to look at the potential for what happens if those flows get reduced in the future due to increased use for reclaimed water, or increased use of reclaimed water and less flow in the river. So we have looked at a future base flow condition that considers what happens if flows get get lower than they are currently from the statistical analysis. Next one. Okay, and so with the design flows, what we're looking to do is produce acceptable velocities through that range of design flows, and typically we would be looking at trying to stay below a design maximum, but the design team has created this table. It's a little more detailed in terms of criteria or velocity bins, and that really gives us the ability to look more closely at things like 2D model results and compare alternatives in the way that they produce the different velocities and the different velocities distributed in the cross section. So it's kind of a way to look at quality of fish passage rather than just judging whether we're successful or not against a single velocity criteria. And I won't go into a lot of detail, but these bins or these criteria are really related to steelhead swimming abilities. And we're going to see these in the 2D model results that Travis Hardy is going to produce later. We've used these bins in order to map the performance of the alternatives for fish passage. And as Wendy said at the beginning, the good news is that we are meeting these velocity criteria. We're showing favorable or suitable conditions for fish passage up to that 1% migration season design flow, high fish passage design flow. And I think that's the end of my presentation. I'll hand it over to Travis.
Great. Let's pause and open it up for 3 minutes of questions. So, does anyone have any questions? I've been responding in the chat. Okay. Oh, okay, we do have a question. Sarah Rascon is asking what our timeline is. And the schedule that we're currently on has us completing our 60% design by the end of the year, along with the initial study for CEQA and our scoping for the CEQA and NEPA. Christine Medic says she really appreciates the division of flows and the rating of quality for each bin. Okay, I think we can move on. I responded to Matali and we can continue in the chat. Go ahead, Travis.
Okay, hello everyone. Thank you for your time. I'm going to talk about the modeling side of everything and how that has helped us evaluate and develop these conceptual designs that Ed was just describing. And as we've been talking about, there's a positive theme. The model is showing us favorable results from the flood risk side and the fish passage side. So this figure right here is just really trying to summarize all this together to explain how we use modeling for each of these aspects of design. We've sort of been talking about this from the very beginning, even the last design charrette, how we really have these two main aspects of the design, the flood risk side and the fish passage side. And there's really often competing goals between the two and different goals. And because of that, modeling was also different for each of these types of parts of the design. So for the flood risk side of things, it's highlighted in green on the left side there. The main model we used for the analysis was a one-dimensional HEC-RAS model based on the Army Corps models. And the model extent was to the entire project reach, the 4.8 mile project reach. And the flows that were modeled is we've focused on the 100-year discharge. This is slightly different from the last time we were using design discharge to start, and we moved into using the 100-year discharge currently, which for this part of our project reach is actually slightly higher than design discharge, so it's a little bit more conservative. And then the valuation criteria for this is really comparing the existing proposed water surface elevations, as we've been sort of talking about a lot. And we've moved into on these final conceptual designs using Freeboard as a main criteria, which we'll talk about more. And then on the FIS passes side, we moved in from the 1D modeling, as we were using earlier, into using a two-dimensional, more detailed model. That effort was led by the Bureau of Reclamation, as we've been talking about. They will present that later in more detail. So one of the big changes to note between the modeling extent, though, is for the 2D FIS passage models, we actually use two subsections of the main project reach. And this was really for efficiency, to zoom in on specific areas of project reach, to test different scenarios and different treatments quicker for this conceptual level. And we'll talk a lot more about that as well later. And then, of course, the design flows were what Ed was talking about in great detail before, and also the criteria with the depths and velocities. Okay, next slide. Okay, so just an overview of sort of what where we started and where we're at now. I'll go through this quickly because Ed just basically summarized this, but we started with using the 1D subsection for these concepts. And as we talked about before, we have sort of these different aspects for flood risk and FIS passage. And one of the main sort of phenomenon that we've been talking about is this whole hydraulic jump phenomenon in hydraulics, where since this flow regime and flood risk level is at supercritical flow, if enough roughness is added to the channel for FIS passage, it could have a negative effect on flood risk, in particular if the flow does cause this hydraulic jump to occur. I put this picture in the bottom right here, just for those of you that aren't familiar with this type of thing. It might be helpful for a visual. Just keep in mind this is in a lab and is a very extreme scenario. It's just to get the point across. But basically, this is water flowing from left to right. On the left side of the picture, there's very low depth and high velocity, and you can see very smooth flow. And then this hydraulic jump occurs, which you see is a big turbulence rise in water surface there. And then downstream there's higher depth and lower velocity with a lot more turbulence. So that's sort of what we've been talking about with this whole hydraulic jump phenomenon. So the final concepts we ended up with, as we talked about, really some of the things that geared the changes was when we translated everything from a sub-reach to the full 4.8 mile project reach, considering bridges and transitions with up and downstream existing channel, and we really converged on concepts that were more uniform throughout the project reach, which has helped us a lot with achieving our goals for FIS passes and flood risk. And the next steps for this flood risk analysis will be to perform a full risk and uncertainty analysis from the Army Corps in the next steps. Okay, so next slide. So as we were talking about, so one of the criteria we have for the flood risk is freeboard. Just a reminder for some people that aren't familiar. Freeboard is simply the distance between the water surface elevation at a particular flow to the top of the channel bank. So if there's more freeboard, there's more space between the water and the top of the bank. And obviously, if the bank is being overtopped and flooded, then that violates the freeboard, and there is no freeboard, or negative freeboard, I guess. So what we were based this off of was just some very general freeboard guidelines from this Army Corps report, summarized in the table below. Basically, the freeboard allowances range from 2 to 3 feet for rectangular concrete channel, trapezoidal, and having a levee or wall. And these all do occur within the project reach. What we ended up selecting for our design criteria for the conceptual design was 4 feet, just over these allowances slightly, just to give a little bit of a buffer. And then a secondary thing that we did, as we've been talking about, is we also tried to avoid having hydraulic jumps occur as well, even if that freeboard was still met with hydraulic jump in areas that have a large freeboard available. We still tried to avoid the hydraulic jump, assuming that would violate the criteria of the flood and risk and uncertainty analysis. Okay, next slide. So this figure right here is the existing conditions freeboard. The x-axis is the river stationing. This matches the arbor study stationing. This is our project reach, and it's going from upstream to downstream from right to left in the plot. The y-axis is the freeboard height with the current modeling. The orange lines here are the left bank of the LAR and the right bank. So for the most part, you can see those are the same because the left and right bank are at the same elevation, but there is a few areas where they are different. The grade line, dashed line is our 4-foot design criteria that we're looking at. And then of course, 0 would be at the channel, top of banks of the channel. So as you can see, moving at the start of the project reach, so on the right side of the plot, this is the transition from the soft bottom into the concrete line section of the channel. It is subcritical flow in the soft bottom and then transitions at the concrete line portion into supercritical flow. So that's why we see this very low freeboard and high depths because of the high depths at the top. And then you get a lot more freeboard as the velocity accelerates and the depth goes down. And then as you can see, moving through the project reach, from a very positive side, you can see on average that the freeboard height is sort of somewhere between 10 to 15 feet for much of the project reach, which is a lot of freeboard and gives some breathing room for the design, which is a very positive thing. And I guess the only area that truly violates this, our freeboard target, is that transition area up top. The one last thing I'll say is the one dip at 7th Street further down in the orange area is something we're looking into to verify that's correct. It does, the channel bank is lower that we can see on the left side of the channel there than the right side, but if it's that much, we're looking into further. Okay, next slide. So just as a reminder of what these our concepts are here to move into results after this. So this is our concept A, that's 40 feet wide, 44 feet wide and 5 feet deep, generally with asymmetric channel. Then next is our concept B, which is just slightly wider and shallower, 60 feet wide and 4 feet deep. Okay. So for the flood risk, so the final conceptual 30% flood risk modeling, we had 3 total model runs. The concept A, as we saw, the concept B, and the maximum concept, as we've been talking about. So for the concept A and B, they're very similar. Those concepts are generally follow the existing channel alignment throughout the entire project reach. But then modifications were done at bridge openings or bridge crossings, sorry, to mainly decrease in cross-sectional areas to avoid hydraulic jumps and to have less constriction at the flood level. And then these model runs also included the modifications in the subsections from the 2D model, which we'll talk about later. And then our maximum concept just used the concept A throughout, but it really, the changes were at the piggyback yard area where we added the channel expansion upwards 1,900 linear feet from the channel bank. And doing this, we followed the modeling technique that the Army Corps used in the armor study, using expansion and contraction ratios to model the expansion area. Next slide. Okay, so the last thing before the results that we did to produce for the modeling is the bridge modifications. This is a large table, but just wanted to point out a few things here. So the left column of this table lists all the bridges that are in the project reach. And there is a total of 19 bridges in the project reach. So obviously it's a very big part of the design. And from the last design charrette, one of the main things we did was look at each of these bridge crossings individually. And we did things like document the number of piers, the pier width. One of the main things that came out of this was looking at the maximum opening that's allowable for low flow modification based on the location of the piers. As you can see in this table, in the third column there, the smallest width that we have is 76 feet opening. So that helped influence what we decided for the dimensions of our concepts A and B to be able to fit through that opening and have this continuous low flow modification throughout the project reach. And then on the right side is concept A and B. This is a summary of the modifications that was done in the 1D model in order to mitigate flood risk impacts and not cause hydraulic jumps from constrictions. The main thing I just want to say about this is you can see for concept A that there's 4 total bridges that needed modifications, but moving into concept B, there's many more, and a lot more modification was necessary in order to meet the same goals. So I think what this is really helping us do is narrow down on the dimensions of the low flow modification channel that will be the most efficient at meeting the goals of flood risk and fist passage. Okay, so next slide. Okay, so I just like to run through some of the results from this analysis now. So this is the water surface profiles for each of the concepts. So this one is showing the existing versus proposed for the concept A at 44/5 channel at the 100-year discharge. So the x-axis is the same as before, is the river stationing upstream to downstream from right to left. Now the y-axis is the elevation in feet. So the orange lines here are the top of banks of the LAR channel. So that, as you can sort of tell, follows with what freeboard output is. And then the light blue line is the existing conditions, water surface, the dark, and then the corresponding gray solid line is existing conditions, invert or channel bottom elevation. And then the dashed lines are the proposed conditions. Dark dash line is the proposed concept A water surface elevation, and then the 5-foot drop channel, that's the dashed gray line. And this theme will continue through the rest of the plots, so you're aware. So a couple things to point out on this. Again, at the top, we have this transition from the soft bottom to concrete and having that large depth that does go and transitions into supercritical flow, and then it remains basically in supercritical flow throughout the project reach under existing conditions. And therefore that basically limits us in the proposed conditions to do the same. So with these outputs here, you can see there's a few bridge areas that are called out with the arrows at the bottom that were the most constrictive bridges. The little bumps in the profiles are because of the constrictions. A lot of those are being seen in the existing profile. And basically, with added roughness, it's pushed it enough of constriction to cause a hydraulic jump until modifications to increase cross-sectional area were added. But with those, from a very positive note, we were able to get rid of all those and decrease the water surface in those areas with modifications. The last thing to notice here is that the water surface elevation is a consistent rise under proposed condition through the project reach. In this concept A, I have it written down, it's on average about 1 to 1.5 foot consistently throughout, but varies from there as well. Okay, next slide. Okay, that did actually change. They're very similar. So this is concept B with the 60-foot and 4-foot channel concept. So as you can see, the profiles are very similar. And when we were able to get rid of a lot of the rises in water surface as well, certainly hydraulic jumps, the results again show a consistent rise. This one is slightly more, as we started hinting at earlier, being a little harder with this increased area of roughness. And the rise is around 1.5 to 2 feet consistently throughout. There is a jump occurring right at the Royo-Seco confluence on the right side there. But we believe that needs further modeling. It's basically due to the limitations of the 1D modeling. We simply have this flow ramping up right there right now, so that needs more detailed analyses to understand what's really going on there. Okay, next slide. So lastly, this is the maximum concept output. This is zoomed in to just the area around the piggyback yard. All the profiles and lines are the exact same. The only added one is the red dashed line, and that shows the proposed condition critical water surface elevation. Basically, all that means is that when the blue dashed line there is underneath that elevation, it's supercritical flow, and when it's above it, it's in subcritical flow. So as you can see there with our expansion, the water surface coming into the piggyback yard area is in that supercritical flow state, and a hydraulic jump does occur through the expansion area and then converges back to supercritical flow at the downstream end. This is consistent as far as we're aware with what we found with the Army Corps' modeling of this area as well. Of course, it will need further investigation and analyses and so forth, but the main point we wanted to get across is that our low flow modification channel, our concept A and B, will fit with very minimal impact to this flood risk into this concept. So they can be integrated very seamlessly. We think that's a very big positive of this. Okay, so next slide. Okay, so just to wrap everything up for the conclusions of the analysis, the concepts A and B are meeting the freeboard design criteria that we sought after. And we are able to mitigate the impacts of the bridges currently with some modifications at the bridges. And we're also getting very favorable results for fifth passage, which we will look at in the second part of the presentation with the 2D model outputs. So that's a very positive thing. And then for the maximum concept, we are not meeting the freeboard design criteria, but this is consistent with what was found in the Arbor study. And of course, as we said, it needs further investigation, but there's, as everybody knows, there's immense possibility of ecological and recreational benefit from this. And then, as we said, we can integrate our concept A and B into this plan with minimal impact. And then lastly, our next steps are to get into a more detailed risk uncertainty analysis to see what this means for that. And that is the end of my section.
Thanks, Travis. So we had questions in the chat, and I know that was a lot of information to present to you within 1 hour. So deep breath, and we have time to just talk through questions now and to kind of talk about other thoughts that you have given other work you're doing. To start us off, Chris Medic, U.S. Fish and Wildlife Service, asked, what is causing the hydraulic jumps in the picture that was shown in Travis's presentation? So let's see. Ed, do you want to try that, or Travis? Go ahead.
Yeah, I actually just got the photo without knowing the rest, but it could be a lot of things. But a lot of those flume studies I saw, they like just put a blockage at the end of the flume to backwater up, and then that sort of subcritical flow propagates upstream. It's pretty cool to see. If you're interested, there's some really cool videos on YouTube that show that phenomenon happening. And it's pretty cool to see. But I don't know exactly in that case of that photo what they added to cause it. But I assume it could have been a blockage at the end of the flume to cause backwatering.
Thanks. So this is Chris. So it was a constriction downstream that was causing this effect to move upstream?
That's just a guess based on other flume videos I saw. It's just like an easy way in that scenario to show that, like, because basically that photo was from it was like a class, you know, just to show that phenomenon to students. It's just an easy way to do it, but I'm not actually exactly sure.
Ed, do you want to jump in? Ed Wallace?
I just say in general, you know, any constriction, even increase in roughness, change in channel conveyance, all those things are things that can give a higher water surface elevation or tend to raise the water surface elevation downstream. And when that happens, you get the hydraulic jump. And so that's why, you know, we have to be very careful about adding roughness. We have to be very careful at bridges, as Travis was describing, because any change can cross that boundary where we have a hydraulic jump and then we have a much higher water surface.
I guess I'll say in the case of our modeling, what we were seeing for hydraulic jumps was constrictions at bridges downstream and then a hydraulic jump upstream of that.
Yeah, that was basically what I was asking. Thank you.
Okay, sorry about that. Yeah.
Kerwin had a good question. He was asking about trash and other debris that may accumulate in the nice pools that we're creating for the steelhead, and how important it is to think about that even now in terms of keeping the water quality up and just being aware of recreational use and other things affecting the steelhead fish passage and pools. So the answer is we will follow up with you, Kerwin, on that comment. We are working with the city and Army Corps and the county on questions about recreational use, and of course the project is integrated in terms of trying to reduce trash to the river, avoid trash at all costs. So thank you for your comment. Did you have any other thoughts, Kerwin?
Well, no, I was just saying that we've seen some of that be an issue here in the Inland Empire with trash accumulation, not necessarily during the wintertime because the high flows tend to flush a lot of that out, but when the flows go back down and you have wastewater discharges, a lot of that stuff just gets carried down from, you know, normal human activity up on the streets above. So we've seen a lot of times when you get a pool where there's some slack water, the trash tends to, you know, accumulate there and pile up, and a lot of it sinks to the bottom. You get people that put shopping carts in there, and you know what I mean? So, and then the shopping carts catches trash. So I would think there would need to be either, you know, a regular patrol of people going in and taking that out, or sometimes they put in trash booms and that kind of thing to catch stuff. But there might need to be an active, you know, line item in a budget or some type of program like you do when you go in and maintain infrastructure. You have a interval period of when you need to do maintenance, and so to me that would be kind of critical, especially you've seen some parts of that river after a storm, the tree debris and stuff. It's like plastic bags, all kinds of stuff. So I would think the pools are great for the fish, but they're going to be little places where trash are going to accumulate. There's going to need to be some kind of program to at least keep it, you know, somewhat controlled.
Great. Thank you. And we will follow up on all of these comments. This is great. This is what we need. And the basis of design report will address these study questions. Sarah Rascon asks, how closely is the study coordinating with the LA River Environmental Flow Study with SCORP? Are they incorporating the baseline minimum flows for this project? Number two, how will the project engage communities and undergo tribal consultation? At which point will engagement and tribes be brought in? And number three, there are large homeless encampments at the confluence. Could this interfere with watershed health and fish passage? Thank you, Sarah. Those are great study questions. So number one, yes, we are working with SCORP and the LA River Environmental Flow Study. And we are reviewing draft reports and other things that are coming out soon and tools that'll be used. And so there is a synchronous amount of work going on between our team and the SCORP team. And yes, the goal is to not have any interference with steelhead minimum flow needs. Number two, the tribal consultation and engagement. FOLAR is on the line. I know they've been working with the tribes, but in terms of a real structured tribal consultation, the city will be embarking on that soon. And engagement is critical in terms of the design process. And so basically it's happening it's happening already, and it's going to continue, but it's going to be more structured when the city does their tribal consultation work with us. And Sarah, we would love to hear more thoughts there. So if you have other things, can you add that? Do you have anything else to add right now, Sarah, about the tribes? I think she's on mute. Okay, no thanks. Okay, and then the large home, yes. So we will, yeah, we're working with the Corps and the county and the city on any things that could impact watershed health and fish passage. And thank you for bringing up the homeless encampments at the Confluence. We will look at that. Other questions? Brian Baldoff said, this is a really great study. Will you be discussing later in the presentation the efficacy of implementing mid-river fish passage versus starting at the mouth and working upstream? I love that question. Yes. So thank you, Brian. Yes. So as part of this scope, we completed the watershed wides, so starting at the ocean and going to the headwaters, the limiting factors analysis, looking at barriers and other limiting factors, next steps. And so this project is mid-river. You are completely correct. We are all looking at it in the middle. So the great thing is leadership. So the city's providing leadership with the Army Corps and the county and everybody, FOLAR, NIMS, CDFW. So we have a great opportunity to work in tandem with other work going on in the lower LA River, the mouth, and in the tributaries with folks like the Rio Seco Foundation, the Tujunga, and other upper tributary work like removing Brown Mountain Dam and other things, resident populations for trout. So thank you, Brian. The answer is we are doing it, working everywhere with everybody, and appreciate more information as we move forward. Joe Gonzalez, Mark Guard. Joe says, is or will fish passage study and concepts be included in the LA River Master Plan update? Great question. Yes, we are working on that as our partners. That's the quick answer, Joe. Mark Guard, are there plans for Coarse-Scale hydraulic modeling of the entire river to prioritize future projects? Great question. Let's see. That sounds like, let us get back to you on that, because I don't have a quick answer to that right now, other than we did take in. Does anybody from our hydraulics team want to try to answer this? I don't see anybody raising their hand. Okay, so Mark, we will get back to you on that question. Great question. It sounds like a next step. Okay. Everyone's quiet now. Other ideas or thoughts or any concerns? Are there any concerns? Everybody giving a thumbs up? They're happy? Okay. Well, I just want to give a chance for others to ask questions. Anybody, I really want you to ask questions if you have questions. No? Okay, I think the long and short of it is, we do know that there are, water reuse projects. There's a lot of water quality projects. There's other habitat projects for Vireo and other species and urban biodiversity and all kinds of things going on in LA. So this project is intended to complement those efforts. And steelhead seem to be a really, they are a great keystone species to help direct, get funding, and integrate with a lot of these other efforts. So that's kind of the takeaway message, and we're so happy that that you're all here and that the flood and hydraulic results are looking favorable for steelhead. So you can feel free to email us if you have other questions. At this point, we are going to we are going to transition into the 1D and 2D backup technical modeling presentation. And so if you want to hear about that, then please stay on. Travis Stroth and Travis Hardy, Bureau of Reclamation, will be walking through that for the next 30 minutes. If you're not really in tune with that, you can drop off. And we will be in touch with you on the basis of design report release this month to get your input on that. Any questions? Good. Okay. Yeah, my camera's not on. I'm all like, great. Okay. Thank you all. Again, thanks for your participation. And we are going to segue now to Travis and Travis about 1D and 2D. I think we're going to go straight to Travis Hardy. Are you ready?
Actually, I think I was going to introduce these.
Oh, you're going to introduce. Okay, go for it.
Okay, thank you. Sorry, I'll stop talking soon, I swear. But just wanted to introduce these subsections here, as we talked about earlier. It's sort of zoomed in and more detailed at specific areas of the project reach. So there's 3 total surfaces, if you will, topographic surfaces that we designed in order to be modeled in 2 locations. So this table sort of summarizes that. The first subsection is near the Arroyo Seco confluence. It goes from just upstream of our project reach in the soft bottom area to the railroad upstream of North Broadway Street, downstream of the Arroyo Seco confluence. In that scenario has concept A, the 44x5 channel throughout, mainly following the existing alignment. It also has a one way of transitioning from the soft bottom to our design, which is a gradual transition by gradually increasing slope and width until the channel low flow channel notch reaches the 44x5 dimensions over a couple hundred feet, going from the soft bottom area to the couple hundred feet downstream of there. Let's see, the other thing we had is we talked about earlier with these 2 resting pool features at the confluence. And then the last thing we have is modifications at a storm drain to test an idea of connecting to an existing storm drain to provide fish passage flood refuge, which we can look more in detail what that looks like here. And then the second subsection was for First to 4th Street. It was just upstream of First, downstream of 4th Street, further down in the project reach. And these 2 subsections, or this location had 2 different scenarios. One was the concept A again with the 44x5 channel, and the other was concept B, the 60x4 channel. We sort of strategically tried to test as many treatments as we could in these subsections, just to get an idea of what they would mean moving forward for the entire project reach with the more detailed 2D modeling. So for the concept A at this location, The main modifications besides the channel itself was at the First Street Bridge, which is right in the middle of this subsection. And basically, we tested some of these ideas about increasing cross-sectional area under the bridges, as we were talking about earlier, to reduce that flood risk impact, which we'll get into what that is here in a second. There was a little bit different modifications for those two scenarios. Okay, so next slide. So just give an overview. This is our more engineering plans for this, that it's a little hard to see on the scale probably, but just to get the idea across of what this looks like for these subsections. The picture on the left is the Arroyo Seco subsection that starts up there at near the soft bottom transition, and then Arroyo Seco, and then slightly downstream of there. I don't know if people could see my mouse. I kind of doubt it. So I'll just try to describe it. So the red squares there, the dashed lines, thank you, Sam, are the two zoomed in areas on the right side there. The first one is the two pools at the Arroyo Seco, which we sort of saw already. Of course, the idea of these are to have a vertical and horizontal expansion into the pool to provide enough depth to hopefully provide overhead cover for fish and slower velocities for resting. The expansion on the right side of your photo, or river left, because flow is going down on the screen, would provide a back eddy type flow area that has slower velocities for the holding habitat for the steelhead. And then the second square further down is the storm drain area. It looks a little interesting on the scale here, but I can try to explain it. Basically, there's an existing storm drain on the perched up on the bank. Thank you. There, that when flow comes out of it, just runs down the bank. And the idea is to cut a notch into the bank there, and therefore create a vertical wall there at where the stormwater would drop off of. And the idea with this is when flows get higher and higher, this can possibly create a pocket of slower velocities for flood refuge for the fish that are even higher than our fish passage design flows. And then the rest of the area there that peculiarly looks like crop circles or something are actually pools. And these are connected at even lower flows at the low flow to the low flow modified channel to provide resting area off to the side of the channel and a sort of pathway for the fish to get from there over to the notch as flow increases during a flooding event. That's the idea. Okay, so next slide. So this is the First 4th Street location now, and this is the Concept A one. This one is simpler to some degree. It's basically just the low flow channel through this area, and then extra modifications at the First Street Bridge there. So the red square, again, is delineating the zoom in area on the right. So in this area, again, flow's going downstream. On the left, your right side of the low flow channel, there is a notch that's added to add extra cross-sectional area. And then on the right side, you can see another larger notch. This is another idea of increasing cross-sectional area by actually cutting into the bank and creating a vertical wall through the bridge. And in this case, it's 6 feet total height, and then smoothly transitioning and tapering that off as you go downstream. And again, that's just for cross-sectional area for the flood risk side of it. But of course, we wanted to see what that did and how it influenced the fish passage side of the hydraulics as well. Okay, so next slide is very similar. It's the same location, except this time it's the Concept B, the 60 feet by 4 foot channel. And same thing, except in this case, we followed the existing alignment. The last one, we actually pushed the alignment over to the right side. That was just to test what it would be if we did decide that changing the alignment would be beneficial enough for things like shading and so on, what that would look like in the model as well. So just again, testing as many things as we can in these subsections. So zooming into the right side again at the First Street Bridge. The channel is now on the left side of the bridge opening, the modified low flow, and you see that same cut into the bank on the right side of your screen. And that actually goes up to 10 feet in this case, because again, the Concept B needed more area to mitigate that flood risk. And then we also tested this idea of adding a split flow channel around the other side of the bridge pier. And the idea with that would be, it would be concrete still and not roughened. It would be solely for increasing cross-sectional area, again, for flood risk. But again, just to test what it means at the fish passage flows. Okay, so with that, I'm gonna hand it over to Travis Hardy to talk about the 2D modeling results for us.
Thanks, Travis. Thanks everyone for sticking around for some 2D modeling results. So as Travis mentioned, we broke the project reach into 2 subsections to better focus in on the fish passage with the goal of highlighting the certain hydraulics, mainly velocity and depths, that pertain most to fish passage. And so we used SRH-TDH it's a depth averaged model. We analyzed 9 separate discharges. They're all steady state. Ed talked about those 9 discharges earlier. And so we ran those 9 flows for the 3 scenarios Travis just mentioned. And so just a little background, 2D modeling. We took the design services that Travis was just showing. That becomes like the topography or the surface that we use to create our mesh. And these reaches are kind of interesting because there's trapezoidal sections and then there's vertical walls. And so vertical walls are meshed just as the model boundaries. And the way we modeled roughness for this analysis was with a depth vary roughness within the low flow channel, with the idea that we're going to be adding cobbles and boulders into the low flow channel to create the roughness that will hopefully decrease velocity and increase depth. And then elsewhere on the existing concrete sections, that's going to be a smoother roughness. So with the idea that it will be able to maintain that ability to pass flood flows. Okay, Sam. And here's the slide again, highlighting the hydraulic criteria that Ed mentioned earlier. It's color coded based on the bins. So resting is a kind of optimal, and then that's the lighter color. And as we go towards the darker colors, velocities are increasing and the colors are becoming darker. So just keep that in mind as we look through these results. And the other thing I want to mention there is that we're clipping everything to a foot or greater. So we're just assuming anything less than a foot is not suitable for fish passage. And so just to briefly describe how we apply the model, we take the model inputs, we run the flows, the 9 different flows, and get a result for each one of those for each section. And those model results are for the whole flow range and all the hydraulics. And so after that, we take those results and we clip it for it's about a mile long area of interest polygon, and we filter out for depth, like I said earlier, and then we bin every element in the model results and put them into those velocity bins and color code them so that we can look at them spatially, and then also in GIS where we can analyze what that looks like. We can put the next slide. Okay, so here's what the distribution of the velocity looks like. This was not clipped, so this is kind of like raw 2D model results. The velocity is shown in blue, is very low, just below 1 foot, and then up to 17 feet per second is what we're looking at here. And so I just want to show this so people get a general idea, because after you filter out and put the velocity in bins, it's harder to get the whole idea of the distribution and how the flows are going in the overall channel. So concept A there on the left, you can see that it's kind of the lighter yellow and blue on the river right, which is where the low flow channel is. And then on the smooth concrete on the river left, you can see that it's high velocities in red. And so what we're trying to do is optimize that river right section, the low flow channel, to potentially slow down the flow and create some area available for fish passage. Concept B, as Travis was saying, is kind of, it flips to the other side of the river, the low flow channel. So now you see the blue on river left. And then the Arroyo Seco is kind of interesting. You get some high velocities coming down the Arroyo Seco. That's just, it wasn't the focus of our model, but it's still modeled just as concrete, so you'd expect it to be really high up there. And then because of the confluence, you get some backwatering, and the flows are slowed down upstream of that. It's that blue section above the confluence. And then you can also see the two pools down there with some lower velocities. Yeah, thanks, Sam. And so it kind of highlights that pretty well in these figures. This is for the highest flow we modeled, 6,500 CFS. So you can skip to the next one, Sam. Okay, and so what we saw before was the full distribution of flows, and this is after we've clipped it to a depth of 1 foot and then put all the velocity into bins. And I'm just using this as an example to show you what it looks like. We'll look at these spatial plots later on as well. Yeah, and so as you can see here, it looks like the flow is only in a certain portion, but that's because we've clipped it based on a depth of greater than 1, and velocities, if they're greater than 10, we've clipped them out as well. And so now you're only seeing a partial extent of the actual wetted channel right now. And to highlight, if you look at the Arroyo Seco again, at those pool areas, you can see that the resting, which is the lighter color blue in the middle of those pools there, is highlighting. And then around that, coming out of the confluence, you get some of those higher flows in the marginal range, 8 to 10 CFS. And that's typically over the smooth concrete. And we can switch sides. Thanks. So here's a zoom in of that, just to give a better idea, some more higher detail. And this time, we're still looking at the confluence of the Arroyo Seco, but we're looking at 3 different flows. And so at the low flow on the left, it's not low flow, it's a kind of a mid-range flow from what we modeled, but 595 CFS. You can see, you really see the extent of the resting area and the pools there. And above the confluence, you can see there's a strip of resting area, resting zones that goes up the river left side of the bank there. And that's typically what we're going to see throughout these reaches, where you have the somewhat shallower flows on the margins of the trapezoidal low flow channel, which provide better fish passage. And so as you increase flow, you see some gaps in there that look kind of funny. That's just because we've clipped out all the areas that we're considering not suitable. Okay. So this is a cross-section area view of concept B. We're moving to the 1st to 4th Street just as an example of kind of some flows and how that looks like in the channel. So on the lower plot, we have bed elevation showing the channel, and then I've plotted 4 flows on there. And so you can see at 600 CFS there, the flow is mainly contained within the low flow channel. And so you'll get some of those shallow areas and within that low flow channel. But it's utilizing that asymmetrical channel design to create some diverse velocities and hydraulics in that low flow channel. And then as you increase the flow, we're going to start spreading out over the entire channel. So the next flow is 1500 CFS, and that, while it's not within the main channel or the low flow channel anymore, we kind of have jumped out a little bit, and it's still not deep enough for fish passage. It's less than a foot deep, but you can see that it's started to spread out over the entire channel. Whereas once we're getting these other flows for 4600 and 6500, the depths are greater, but outside on that smooth channel, we're seeing some pretty high velocities. And so, yeah, just some how the flow as the flow increases, what it looks like within the cross section. And then the velocity plot on top, if we look at the low flow, the 595, we can see that the velocity varies across that low flow channel. And that has to do with the way we modeled the roughness as the depth vary roughness. But you are seeing some lower velocities over in the shallower side of that low flow channel. And then the other 3 plots there on the velocity show that in that smooth concrete section, we get some pretty high velocities. And then they dip down where we have the roughened area in the low flow channel. So just trying to highlight that, but it looks like within a cross section there. You can flip the next slide. Okay, so we took those spatial plots of each hydraulic velocity bin for all the 9 flows at each of the 3 subsections, and we threw it into GIS and ran some summaries on them based on area. So this plot is showing the 9 discharges from very low to 6,500, and then area on the y-axis. And if you focus on the 25 CFS, the 3 concepts, you can see that the areas are pretty low per 1,000 foot stream length. And that's because it's all contained within the very bottom of the low flow channel. And what that's showing here is that all the area that is within that low flow channel is showing as resting velocity speed, so in that 0 to 2 foot range. And then as you increase flows going across the x-axis to the right, all those same colored 0 to 2 foot resting zone is pretty constant throughout, up until maybe like 1500 CFS, where they start to drop off a little bit. But what that's saying is throughout these range of flows and all 3 of these design scenarios, we're having some areas of resting, which is good. And then if you look at flow 128, you start to see some zones in the 2 to 4 range, which we're calling favorable fish passage. And that's just you're increasing the velocity, and so you're also increasing the area because you've added flow and the depth has increased. And so we start to see that area increase. So as we go to the higher flows, we get more and more area as we add more water. And then what we're seeing there is that up until 1500, all of the flow is within that channel is still relatively good for fish passage. We have resting, and then we're all in the between the 2 to 4 range, which is good to see. And then at 1500, that's where we see the areas jump, the total area. really spikes there. And that's where we saw in the cross-section plot where the depth finally jumped out of the low flow channel. And so now we're seeing some of these higher velocity zones in the 6 to 8 foot range. Yeah, and as we increase the flows even further, we start to see a drop in the resting area, but we're still seeing some good suitable flows and some good areas of it's the favorable zone. So that's good to see in those as well. Switch to the next slide. So here's kind of the same exact idea, just with a simpler plot to kind of highlight those trends again. So this is at concept B, which is in the 60 to 40 or 60 by 4 foot section down in the 1st through 4th Street. You can see the light blue section, 0 to 2 foot resting area is pretty constant, like I said before, up until like 8:30, 1500. And then through those main mid-range flows, we're seeing lots of favorable fish passage, which kind of starts to drop off at those higher flows. And then you can also see that spike at 1500 with that range of 6 to 8 feet per second. So this plot is showing that for a good range of those flows, we're seeing adequate velocities. And again, breaking out those area discharge curves based on each, and then being able to compare each concept for a single velocity bin. And it's kind of highlighting the different concepts against each other. So if you look at the top two plots, concept B is that blue line, and it's the blue dashed line, and it's slightly above both the other scenarios, the other concepts. So that's kind of helping us pinpoint that maybe the wider depth of the wider width of the 60 by 40 channel is providing some of that extra area for suitable fish passage. You can switch slides. Thanks. And so looking at areas is a good metric. You get numbers out of it and you can compare it on a plot, but realistically, there's a lot of things that go into what contributes to fish passage. And there's temperature, there's behavior, there's all kinds of different things that go into it. And one of those is connectivity. So in order for a fish to swim from downstream to upstream, it's got to have some kind of longitudinal connectivity from those 2 points to be able to migrate upstream. If there's barriers, then obviously they're going to get trapped. So what we're trying to do here is analyze these results spatially to see, what kind of connectivity we have throughout the length of the reach. And these are a little hard to see, but for 595 CFS, through the different sections here, we're seeing that the favorable discharge in that low flow channel is pretty continuous throughout the whole reach. And then on the margins of that, on each side of the low flow low flow channel, you see like a very tiny sliver of resting. And so that's obviously a pretty coarse 2D model result, but it's showing that I think that resting area is a possibility in those margins. And then in the Arroyo Seco, we see those pools again that we saw earlier. And then as we increase flows, we're seeing a little bit more fragmentation, whereas in the lower flow, we were seeing pretty much just straight favorable velocities. Where now we're seeing some of that suitable range pop into that low flow channel area, but still pretty good connectivity within that favorable range, which is good to see. And this flow at concept B kind of highlights that side channel under the bridge that Travis was talking about. Because it's not roughened, you see, thanks Sam, you see that it's in that high velocity range. And so it's just kind of highlighting the difference between where you have roughened channel for fish passage and where you have, smooth concrete. And yeah, again, in the Roa Seco, those pools at the bottom are maintaining some good resting zones. So increasing flows again, we can go to that 6,500, Sam. Now we're still seeing that connectivity in the low flow channel. However, the suitability bin has been raised to the suitable zone, but it's still all very connected. And this is the highest flow we modeled. So I think that's a pretty good result right there. And then the Roa Seco is interesting because we see some zones in those pool areas with some lower flows, some lower velocities, and upstream of that, which is also promising. And so Travis was talking about the wall cutout before, and what we wanted to see here was how that worked at these higher flows. And so at the lower flows, we can see that, yeah, here's the photo or some zoom ins at that wall cutout storm drain. At the 595, we see that there's a good amount of resting area in that cutout around those pools. And then as you increase, you lose some of that resting zone, but we're still creating some lower velocity zones. And as we go to the highest flow, we're kind of washing out the benefits of that cutout, which I think is something that we can improve on. And I also don't think that a 2D model is necessarily doing it justice there. If you have a deep cutout there, you're going to see some flow towards the bottom. This is a depth average model, so there's no variability in the velocity in the vertical direction. So this might not be the most telling for this scenario, but I think it is promising that we're seeing that resting in the lower velocity zones at those lower flows. I think it's a viable option, I think, is what this is showing. So just want to save, we got 10 minutes left, so hopefully we have some time for discussion, but I just wanted to sum this up with, looking at the trends between the fish passage as a function of discharge for those three flows. And I think what the results show is that we're providing resting zones for the majority of those lower flows, and we're providing suitable zones of fish passage for the majority, for almost all of the whole range of flows. The 60-foot wide concept B, we're showing a slightly greater area for fish passage, which makes sense practically and theoretically. So that's good. And but it also points to, obviously there might be a cost benefit ratio that you want to look at there, but it does look like it's providing some more area for fish passage. And overall, through spatial analysis, we could see that connectivity was, I think, achieved for most of those flows. If you look at the figure on the right, we see some areas where velocity is not met, but those are over short distances. And I think we can either improve on this through design to get full connectivity, or I think it's also, I might get in trouble for saying this, but there's potential for burst swimming through smaller zones like this, but hopefully we can get through to that. And so I think the main thing to consider moving forward is is looking at those pools and how to optimize those, the pools and the side cutouts, and how to optimize those within the whole entire reach to be able to provide some resting zones in between throughout the reach. So
Thanks, Travis.
mhm.
Okay, so we've been having some good chat while Travis has been talking. And so I'd like to wrap some of that discussion and then also open it up for more questions. So just to recap the questions that have been going on during this presentation, the second half, Chris Medic and Christian Romberger have been asking about the pools and asking our team to consider the holding pools in terms of making sure fish don't get trapped in the pools, depending on the flows. And Ed addressed that question, saying that there's always some risk with pools, but configurations, you know, are considering how to minimize entrapment. And then connectivity between the flows from the tributary need to be focused on. And let's see, yep, Christian Romberger was talking about, of course, we know the Arroyo Seco has habitat upstream. So any connections with the pools, there is a low flow notch, but making sure that from a fisheries perspective, the velocities and the confluence are really carefully studied. Tim Brick is also asking really good questions about modeling. And it's a really good basic question. So the modeling that's being presented does consider the confluence, and we know about the Arroyo Seco restoration with the arbor and the, you know, the core. So his question has to do with, why is the modeling all focusing on concrete at the confluence when the arbor is a naturalization where concrete is removed? And let's see, I just want to capture more questions before we get into it. Mark Hanna, it will be interesting to see how the deepened low flow channel behaves up to 4 feet deep, behaves in both wet and dry weather conditions with groundwater depths and at transitions at project boundaries. Thank you, Mark. Okay, so I think folks can talk. So who would like to speak up? I just kind of reiterated a bunch of questions, but Tim, did you want to say anything, or Christine or Christian or Mark? Do you want to just speak yourselves?
Yeah, this is Chris. So I was having a little bit of hard time following all the modeling figures. So I'm not sure if I missed this, but it looked like there were separate pools being proposed at side drains in addition to the confluence at Arroyo Seco. And in some of the figures, I think they mentioned they look like crop circles. It looked like they were, you know, relying on flows from drains, and that then they would go into a pool, but there was no connection between that pool and the low flow channel that was going to be created on the other side of the river, right? So my concern was they would function in higher flows, but then once the flows recede, the fish could get stuck and be separated from the remaining, you know, water channel in the main stem. So I was requesting that you look at, you know, what are those low flows from those side drains that would allow for continued, you know, connection between the side drain and your proposed low flow channel, if there could be a connection made there.
And cancel before there's too much.
Great. Okay, that's a great point, Chris. And Ed or someone from the design team, do you want to address that quickly?
Well, I'll
Or
just
shall
say
we
that,
get back to Chris?
yeah, we can get more details, but just say that trying to make that connection between any pool that's created at a storm drain outlet and the low flow channel is something we are thinking about. I'm trying to make the configuration so that there is some drain back to the low flow channel in the center of the channel. It's always kind of a trade-off between, you make the pool a little deeper, you get better resting habitat, but you also increase the potential for entrapment. So, some combination of being able to drain back, maintain that connection, and not going too deep, so the fish have a clue that it's time to leave the pool. But it's definitely something that we're thinking through on all of these pools.
Great. That is kind of getting at the heart of these designs. Thank you, Chris. And we will be following up. Okay. Christian, did you want to say anything more?
No, I think my concerns were addressed pretty well. I appreciate it.
Thank you. Okay, and we will continue to follow up with you, Christian. Mark's question, does Ed or anybody want to address that one? And then there's a question from David Crowder.
I think Mark was pointing out that there, or maybe pointing out that there could be groundwater effects here. The low flow channel will have to be designed to avoid uplift pressure, and there could be the potential for groundwater to enter the channel. I think hydraulically, we've seen kind of how it performs through a range of depths and flows, but yeah, it's a good point that flows in the channel could be affected by groundwater.
Thank you. Mark, did you want to add anything else? Remove. Okay. David Crowder asks, what about a 3D model to help create determined resting areas? Something that 2D models cannot reveal.
Yeah.
David, I was thinking, specifically if you're having trouble meeting the 1% during the migration season passage,
Right.
That, typically we're looking at depth average velocities through the 2D model that, for very short reaches, it may be possible to create some, boundary layer effects that would be suitable passage, but would only be revealed at, a 3D level. That was kind of my comment.
Yeah,
Right.
I agree. It kind of highlights that the limitation of the 2D model, and maybe, if there's pushback, or if we don't think that the 2D model is adequate, then 3D would be the way to figure out how to make that work. I agree.
All right, thanks.
Yep.
We are seeing, though, David, pretty favorable results up to that 1% migration or 1% exceedance in the migration season. So we're pretty pleased with that.
Yeah, I just, so my question was, are you seeing that pretty much at all of the locations, or do you have any particular spots that you're really concerned about?
Well, I think you saw in the simulation results there that we have a little bit of a hot spot right at the confluence. But I'm pretty sure that we can make some adjustments there and reduce or improve that one. But in general, I think we've kind of reduced the number of abrupt transitions, and in general, these typical sections are doing a good job, as Travis Hardy said, of providing continuous flow paths at that 6,500 CFS flow.
Okay. Yeah, I was just unclear, you know, you have such a long reach and so many bridges and things like that. I wasn't sure whether you were, maybe I missed it, but whether you were just highlighting these two locations as, you know, the biggest problem spots, or whether there were some others that you just didn't go into today.
Yeah, so far, as Travis Strauss said, we've taken 2 sub-reaches and applied the 2D model, done the terrain development, applied the 2D model in those sub-reaches. And the typical sections have been adjusted a bit to sort of fit through the majority of the bridge opening. So we've reduced some of the transition problems that way. But for sure, you know, as we look at the whole reach, we may see locations that require a little more evaluation to, or identify places where we don't have you know, a continuous path or a continuous favorable path, and in that case, yeah, I appreciate your comment about a 3D view. A 3D model could maybe give us a view that we still do have passage at that flow.
Great. Okay, let's get to Tim Brick's question. That's a really important one. And then Robert Henderson has a question about flows. So any number of folks, would you like to weigh in on the naturalization of the arroyo as part of the arbor, and why our modeling only focused on concrete? Don't all speak up at once. I think there's a couple of things at play. Let me just say this. The Army Corps is working, I know I've heard that they are working, I believe it's this year, on the Arroyo Seco Confluence Naturalization Arbor piece. I believe in 3D. I'm not sure. Tim, it's not currently part of our scope to go up the arroyo and to focus on that. Our scope does include a max treatment that involves naturalization. What you're seeing is for flood flows, trying to hit our metrics, the doubling and tripling of the channel, concrete channel width for fish passage, and deepening by the same. So it's quite extensive to try to meet the flood constraints at that location, along with fish passage hydraulics. And so that's what you're seeing in terms of modeling right now. That's not to say that we're not going to integrate with the Army Corps on their naturalization. That's kind of just real high level. I don't know if Tim's still on.
Yeah, I'm
Tim?
here.
Okay.
Here. And, you know, that addresses my concern. I just want to make sure that we're not, you know, there's the hot spot that's been identified. There's other measures that can be taken at the confluence, which is part of the Army Corps LA study program.
Yes.
And hopefully the two will be integrated together in a coordinated way rather than just proceeding, you know, with two different design teams that are
right.
not talking to each other.
Absolutely.
And you know, that's kind of my concern about it. So
yeah,
thank you for addressing that.
Yeah, no, we are talking. It's we're a little ahead in terms of our design modeling process, but we are really trying to integrate. So yes, sooner rather than later. All is good. Okay, let's go to Robert Henderson's question about flow. Robert's still on. He was asking about how often would 6,544 CFS be exceeded? Did you model flood flows in 2D? What results compared to the 1D model? Okay, hydraulics team, what do you think? It's Ed, Travis, or
Yeah.
Travis?
Yeah. Yeah. Yeah, so the 6544, if I'm not mistaken, is the 1% exceedance for the migration period over the winter. And that's why it's a little higher than that 1% exceedance of the annual flow record. So it's just looking at the flow record of the winter period and exceedance probability of 1%. And we did not model high flows in 2D. The highest model that highest flow that we modeled was that 6544 that you mentioned yet. So we don't have any comparisons with the 1D as far as that is like the 100-year. But it's likely moving forward that we might need to do that, obviously, to capture the complexities of what happens at those type of flows.
Yeah, just to put that 1% statistic kind of in more real terms. So the migration season is, I believe it was December to June. So 7 months, 210 days, so 1% of the time, 2 days per year is about the frequency that would be exceeded on average.
And those are based on mean daily flows.
Right.
Yeah,
Does that answer your question, Robert?
Yes, thank you.
Awesome. Other questions? I don't see any others in the chat, I don't think. Rosie says, thank you. All very interesting. Okay, are we done with questions? Raise your hand if you have a question. No? Okay, I think, somebody says, thank you. Okay, well, we're gonna close this out then. Thank you all for your dedication. I know you're all working really hard on different projects, restoration, fish passage, steelhead, outreach, all kinds of things for water. So thank you all for your science and engineering and planning and help management. Thanks again to the Wildlife Conservation Board, Council for Watershed Health, the Mayor's Office, and City, County, Corps, everybody, Bureau of Reclamation. I'm leaving out a lot of people, SCORP, FOLAR, ASF, and all of our partners, the tribes, and our community. We are very excited about this moving forward, and we will be in touch with the basis of design report, incorporate your study questions, and keep on moving forward. So thank you all. Have a great rest of your week, and we will see you again soon. Bye-bye.
Thank you. Bye-bye.
Thank you, Wendy.
Thanks, everyone.
Bye.